Thank you very much for the introduction, and thank you very much for a kind invitation to Lumini by Rafael Danshan and Silka Chasova. Actually, I came here I think 12 years ago in different conference. At that time, not so many buildings here, and then now I think I find many new buildings here. And the life is here very nice, and the food is wonderful. Also, I have some problem in my leg. I cannot climb that mountain, but the mountain view is very nice. So let me start my talk. My talk is based on the joint work with Professor Senjo Shimizu. She's in Kyoto University. I think she has already talked in sometimes in this conference. So my problem is that, consider the abstract Cauchy problem of parabolic type. And then initial data is so far, I just assume that this is 0 for simplicity. And then let's X the abstract balance space. And then we consider the Spokane space of time interval upon X, where I is a time interval. And capital T might be infinity. And if the external force, given external force satisfied, that belongs to this Spokane space, then the maximal regularity said that each of terms of the left-hand side belongs to the same function class. Where A is like a negative Laplacian or Stokes operator or whatever, like a second order elliptic operator, belongs to the same function class. That's I call the maximal regularity, or for simplicity MR. Can I move this way? Okay. 順番間違えるとダメなんだね。順番間違えるとダメ。上止まるのか。Okay, you can see that. And general theory said that if the theta is just between 1 and infinity, suppose that X is so-called UMD. It's an abbreviation of unconditional multi-general differences. Definition is that the time Hilbert space is bounded in such a Bohner space. That's the definition. Yeah, analytic way. There are several equivalent analytic definitions, but I only know about that. This is unconditional multi-general differences, which means that the time Hilbert transform is bounded. It's bounded in L theta x. L theta x. Under such a condition, the maximal regularity is well understood if the operator A satisfies the so-called R boundedness, which is precisely the resolvent of the operator, and also the time derivative resolvent operator satisfies certain kind of boundedness, just like Herman-Mikulin type estimate, which is done by Weiss in 2000 in Masanare. But on the other hand, if the X is UMD, it's necessarily the X has to be reflexive. So if you consider the function class which is not reflexive, such as the endpoint space, if not reflexive, then X is not UMD. So therefore, this such nice general theory does not hold. So my question is that what's happened when the X is some particular non-reflexive space, in particular BMO? So what's happened? My question is, such as, my handwriting very bad, BMO. In such a case, we have to think about the maximal regularity independently somehow. And then let me record what is bounded mean oscillation. Of course, most of you know about very well, but let me record it. So the definition of bounded mean oscillation in Rn, if the f is locally integrable, it's locally integrable. The semi-norm of BMO is defined by the supremum, taking the x naught, this whole space, and taking the supremum of some parameter r is 1 over. This is a ball, the center somewhere on the radius r. This means a major ball. And then f of x negative f bar, which means that average over the ball, same ball is finite. Where the average means, of course, that the same center x naught of f of y dy. And then, of course, this is semi-normal. If you consider just constant, this is always 0. Therefore, this is not quite normal. But if you neglect the constant, for instance, you consider the quotient space or whatever, then this is going to be a norm, and then actually BMO is Banach space. However, if you introduce the let's say CV stands for the continuous function vanishing at infinity, and taking the closure of such a norm, so let's call as a VMO. By the way, for Japanese, VMO and BMO is almost difficult, impossible to distinguish. Let me call it as a vanishing mean oscillation, okay? And this is BMO. So this space, the well-known result is by performance time, is that the Hardy one, the dual of Hardy one is equivalent to BMO by performance time. I think 72. And then dual of vanishing mean oscillation is actually Hardy one. The most importantly, the logarithmic function, this belongs to a bounded mean oscillation. However, this function does not belong to a vanishing mean oscillation. Yeah, you can take some power alpha, which is less than 1, then this belongs to BMO. However, power to 1 is not quite. And indeed, obviously, by definition, vanishing mean oscillation is strictly smaller than bounded mean oscillation. Therefore, obviously, this function space is not a reflection. So we want to obtain somehow the maximal regularity of this type is possible or not in such a function class. Let me also recall some other property of the bounded mean oscillation is, let's say, I'm not quite sure if you use it. Yeah, of course, the element infinity function, bounded function, is included. I probably abbreviate this part. And all the BMO function is also embedded into a LP local space where the P is arbitrary. Indeed, a much more better estimate due to the John Nirenberg is actually exponential L1. And this means that all the power of P is possible for all bounded mean oscillation function. And that's why we can say that the famous, これどうやってやったっけな。これを上げて、で、これを下げる。同時に動かない。あ、そう。So the John Nirenberg estimate says in 61 CPM, CPM, that the norm is actually equivalent with taking arbitrary power. Or to px, and then you take 1 over p for arbitrary p between 1 and infinity. This is because of the disembedding hold. And now we may introduce, we can introduce a similar definition of bounded mean oscillation. By simply plugging the average over there in here, then you can generalize, or it's just equivalent norm, but the space is duplicated of f of x, negative f of y, over 2p dx dy, over to 1 over p is also equivalent, because if you plug in the average here, and then change of order of the integration, you can reproduce this one. And if you plug in the average here, two average, positive, negative average, and separate it, then recover the twice of the norm. So this is an equivalent norm. So after introduce this one, we may go through the maximal regularity theorem. So the definition. F is a smooth function which is not only x but also time. The t is belongs to, for simplicity, r plus, which is 0 to infinity, and x is a Euclid space. And f is belongs to L2 of BMO. This looks like a Bochner space by I put a tilde, which is just like a Riemann space. The norm is taking the supremum of outside. Sorry, I made a mistake. This is not outside wrong. But I introduce this function class. If you consider, let's say, this supremum inside of time integration, this is just a Bochner space. But this supremum is just outside. So this is inside out. Therefore, this function class is slightly larger than Bochner space. And it is inclusion strict. This duplicated way is exactly the same as this way. Then our main theorem is これはどうする？これ一番上に上げて。こうして、ほっとけばいくのか。で、これか。あれ？ほっとけばいく？いかない。ほっとけばいく？いかない。Okay. So the main result is we consider the initial value problem for simplicity just heat equation. Then if the initial data is, the derivative of initial data is bounded mean oscillation, the external force is the same function class above. It's a Riemann type space is BMO. then we might find that there is a solution for this equation satisfying the maximal regularity. Holds for certain constant, which is the derivative of initial data of BMO, and then external force. This is true. Actually, there is some freedom for the everything just has a derivative, so we have to assume some restriction for f in certain point, so that the solution is unique. But so far, this because it's derivative here. So constant, that is a freedom of constant actually. But this is our result. So this is, should we theorem? Maybe I put this theorem. Which is due to Senjo and myself. Shimizu. Which has already appeared in the mass nachrichten. Nach 2020. Okay, so let me consider that as we say that this function class is slightly larger than the Bochner space. And if we consider Bochner space, what's happened? Then let's see. Here is a proposition for this space, maybe 1 and 2. And that is certain constant such that the derivative of f and the production of f belongs to the same function class. And suppose that f of 0 x equal to, let's say, for simplicity 0, then we can say that the supremum of the derivative of the function supremum in time, sorry. Can be dominated by the derivatives of f in those classes. So if we consider the Bochner space, for instance, right-hand side, the space is going to be slightly smaller. By the way, I have to make some comment about this. Okay. I forgot about that. So let me go fast, this one. Then actually this can be dominated by the initial value of the f. If we set 0, this has nothing to do, but you can estimate like this way. Here, this has to be the interpolation space between 0 and this regularity, so that this will be infinity and 2. This is endpoint Besov space. However, this function class is slightly smaller than BMO, because this is just like a homogeneous restricting trivial space, and this one, the outside infinity inside L2, so inside out. Therefore, you can say that some estimate this norm of this one can be dominated by Besov space. Therefore, the function class inclusion has an inclusion. We can also, this is true. And then we think about this function class. However, if you consider some application, the motivation is following. is, of course, the Navier-Stokes equation, incompressible Navier-Stokes equation. Which is solvable in the space in the solution is belongs to basically continuous function in the, let's say, BMO inverse -1 or somewhere like here in the Kohotataru result. In, I don't remember when it was 2000 advanced math. However, if you consider the solution class in the Besov space, let's say, then if the solution is, let's say, the solution in certain Besov space, -1 plus p over n on p, and let's say infinity or whatever. And then the endpoint case, because this is the regularity class, and if the p is increased, then this regularity going down. Therefore, the function class is getting bigger. And therefore, the well-posedness is shown somehow between this range by many people like Marco Canone or Fabrice Planchon or just Yomataman. However, the endpoint case, if the solution belongs to endpoint case, which means p equal to infinity, is going to be a -1 with infinity something. This case, the continuous dependence of initial net fell down by the Burgan-Pavlovich, the ill pose. Why Burgan? Pavlovich. Bits. I think 2007. JFA. And Japanese mathematician Yoneda. He also extended the sigma between the Burgan-Pavlovich showed that this result in the sigma to infinity case, and between 2 and 2 is not included. Infinity is by Yoneda, and eventually the order exponent of sigma is fed by Gaussian 1. 2015, I don't remember advanced math. So endpoint Besov space is not quite good for the incompressible Navier-Stokes equation. Therefore, we want to somehow consider the result for the bounded domain case. And the second motivation is actually I don't want to talk this in detail, but one of the application is the Keller-Siegel equation. Some of you have already mentioned about the results. Keller-Siegel equation. The original Keller-Siegel equation is much more complicated, but if you simplify the equation, is somehow parabolic type. You may put some plus lambda, but it doesn't matter, and equal to u, and consider initial value problem. And it is well known that if the tau is infinity case, which is called the parabolic elliptic type, and such a case, and in particular, the two-dimensional case is interesting because it's a scaling invariant case for the L1 is preserving. If the initial data is non-negative, this is preserving. This is a mass conservation law. And then we want to solve that kind of situation by the both of the case. But if we don't have this the first term, then the finite time blow up is well known. There's many people doing, but of course, the Peter Villa and Toshitaka Nagai. We are doing similar thing. But the tau is for non-infinity case, the blow up result is kind of restricted to only, I think, as far as I know, the radial symmetric case. But anyway, so we want to connect both equations. Tau goes to tau infinity, or tau is not infinity case. So passing tau goes to infinity, we want to show that that's such a setting in the two-dimensional case. And then this is the mass conservation law hold. And such a problem was done by Laksitsky. And then Villa and Brandrez. And almost same time, and also Roubaix-Rechet, he's also doing. And then his spell is kind of difficult, I'm sorry. So what I want to get is that, the point is that if the U is L1, this is just a linear parabolic heat equation. Therefore, the regularity of psi is at most psi is not necessarily at infinity, but psi belongs to BMO if the solution of U part is L1. So we want to obtain such estimate such that the tau independent estimate. Then we can obtain the tau goes to infinity when some limit is possible, which is actually done by Kurokiba myself. Unfortunately, he's passed away in 2020. So this is another motivation, but I don't want to go to this direction. So I want to mention about this one. So basically, this is possible, but if you want to generate an analytic semigroup in BMO, which was done by Giga and then Bokad, Giga, and Suzuki. Let me exchange the. どれにしようか。これ、違いか。ちょっとでっかい部分を使いすぎちゃった。So if you consider the heat equation, there is a storm collection with a semi-group of on the maximal regularity things, but on the other hand, BMO has not really good space, so that the semi-group for heat equation, the produce C0 semi-group if the space is BMO. I'm sorry, vanishing mean oscillation. Because this is the continuous function is dense. But the BMO case, we have to somehow extend by using the Hahn-Banach theorem, so that in such a case, the continuity is breakdown, like C weak star continuous. It's the drawback. But all the result here is the same, so the main theorem is also true, of course. Everything just BMO into BMO. BMO into vanishing mean oscillation. It's still okay. And in such a case, the semigroup is going to be C0 semigroup, and indeed that this is going to be analytic in bounded mean oscillation, analytic semigroup, which is done by Bogart. There's analytic semigroup. By Bogart. Iga and Suzuki in Journal of Mathematical Society of Japan in 2018 or something. So actually, their result is very good because they are considering the general domain case, so not the whole space case. So that's kind of subtle because how to define the BMO is a kind of subtle. Because, for instance, BMO space is a non-local functions class. So if you cut off some area, then the function does not necessarily belong to BMO. So, but nevertheless, they are considering this one in the bounded domain case. So let me shortly. Oh, by the way, I have to also mention about the OSHA-Fries result, which I should. どうしようか、あんまり時間かかっちゃうんですね。定義が隠れちゃう。定義が隠れちゃう。定義が隠れちゃう。これ上げておきますか。オートマチックに言ってくれるといいんだけど。なんか取り替えてる時間が随分。Here we go. Okay. I also have to mention about the result of Pascal Ossas, and Fry in 2017. They also show that the maximal regularity estimate hold for the 10th space, the infinity 2, where the norm is with the supremum of x Rn supremum is R 0 to R 1 over B square root of R of B square root of R x naught with f of dx square dx and dt 1/2. And they show that maximal regularity for this space and also applied the Navier-Stokes equation that this tangent space seems to me slightly smaller than our modified BMO space because the logarithmic function does not seem to be included here. So anyway, so let me show how to show our theorem briefly. Indeed, this was actually somehow commented in the Koko Tataru's original paper, somehow implicitly. So the homogeneous case, okay, let me start from the energy inequality for a heat equation. Of heat equation with external force without external, say F equal to 0, then everybody knows about the maybe twice of the derivative of so ds is dominated by initial data square. Then basically we want to localize this estimate for some cutoff function, introducing cutoff function. Oh, we denote eta r, which is just one inside of a half of radius ball, r ball. どうしよう。まあいいか。Let me say that the center is x node. For simplicity, for center is x node. I should put x node somewhere here, but 0 outside. Then we try to multiply this function to the equation and integrate by parts. And then, besides, we duplicate the energy inequality in the x and y variable. Then you simply obtain that twice of integral of t with s x variable negative u s y variable with L2 in certain ball. Can be somehow dominated by the right-hand side, which is also the duplicated initial data. Two or something. Of course, we have a much more error. Error. いっぱいあるけど。Error. However, if you take a supremum in the center of the ball and the radius of r after this, and then you may somehow obtain the estimate for the initial data term, I mean right-hand side in the first term. Therefore, we have a first-order derivative is difference. That's the homogeneous estimate, which is more or less done by Koko Tataru. And originally, Elias Stein's textbook, who's proved the same things in the half-Laplacian, as usual. So we want to somehow generalize this one into for the non-f equal to 0 case. Namely, we just assume that the u-naught case is okay. So let's assume that u-naught is 0 and f is not 0. And do the same things for energy inequality, but in such a case, we have extra term here, to t with f and u ds. And again, we do the duplicated. And then, therefore, the estimate looks like this is x derivative, and this is y derivative. And localize L2. dt. Suppose that initial data 0, the first term disappeared, and we have a coupling term, which is f of is x negative f of sy multiply with some error. Of course, I have to put okay, this is L2, localized L2 inner product. dt ちょっとチョークが短いんでなんかチョーク長いやつないかな。longer choke. Must be longer choke. Ah, here. Thank you. I can do this. Okay, I have of course error, main error because of this error of a cutoff, and somehow we just try to put the derivative here and antiderivative here with this operator and the antiderivative of x f of s x negative derivative y, this operator and the antiderivative of sy with u s x negative u s y dt, because this is a localized L2 inner product, because we multiply the cutoff function twice. And then divided by the L1 norm of cutoff function, divided by, I don't know how to go, divided by L1 norm square of the equation. Then by using a Cauchy-Schwarz inequality, and before that, we have to pass this integral derivative the other side. But the x derivative is just nothing to do with the y variable function. Y derivative is nothing to do with the x variable function, so that it's going to be a slightly simpler. And then this derivative is passing through the other side. Then using Cauchy-Schwarz inequality, then this part will be similar to this part. However, the radius is twice. Then after taking suprema, that going to be the same, so that we separate the second term, the last term, into by Cauchy-Schwarz inequality with small constant in front of derivative of u. So it's going to be somehow the without derivative, but anti-derivative with the this operator. This is or the x derivative, and then y derivative, and then localized L2 with a certain bigger constant, with small constant, with the same, almost same term, with this is x derivative and y derivative, u of t of y. Square of dx. And we have error because we take an integral by parts here, and this derivative is going to be not only u, but also cutoff function here, so we have another error term. And then once you obtain, after this, you divide by this quantity and take a supremum, then the left-hand side and right-hand side is actually same, but we have a small constant in right-hand side, which is absorbed by this term. Then this one has one derivative less compared to this, so that we obtain the second order derivative. All we have to do is just have to control the error term. And in order to do that, we just introduce, because this one, f, this one is error term is involving somehow u subtracting a, u, and what? U multiply the derivative cutoff, let's say. usx minus usy, second order. And cutoff, one is cutoff, the one is derivative cutoff, and x, y. And after that, we integrate. Then we have to somehow control this one, but this one is slightly, how do I say, not top order. So then we just plug in the D-family formula. Here and there. Then finally we have 3 different time integration appears. And we just exchange all the order of integration. Then finally the last term is also can be controlled the same term of here. Therefore we obtain the maximal regularity is possible. Now then, rest of the time I would like to talk about the application. The first application is simple because as the structure of the norm, we may easily show that the singular integral operator in space direction is also bounded in such a function class. Therefore, the proposition maybe 3. That's this operator Rj. Actually, this is also used here. I should have mentioned this one earlier. This is this operator. Then this operator with space-time function in this function class is also bounded. This is easily observed by the structure of norm is quite similar to the usual BMO. Therefore, you can use as difference. And then the singular integral operator type estimate is easy. Therefore, as a corollary from both the result, we may consider the Stokes equation, the divergence free, for the initial value problem of Stokes equation. Then we obtain the maximal regularity for this equation, the solution, in the same class. Oops. R plus BMO with Laplacian BMO with the pressure is bounded by primitive initial data and external force. If, let's say, you have to assume some restriction for external force indeed. And this is true because of the maximal regularity for the heat equation and also the Ries operator, so that we can recover the first two parts. And we want to, if we consider the Laplacian of P, and we want to revert it, and then the pressure estimate is also follows. So as a byproduct of such estimate, we may apply some fluid mechanical problem. It's called the MHD equation. Let me use this one.これすごいな。簡単に消えますね。We don't have any such a system in Japan because it's never dry up in Japan. It's too much humid, so it's almost impossible. But this is very nice. Oh, yeah, very nice. So I'd like to consider an application. The application. Application 2. The MHD equation, magneto-hydrodynamic MHD equation with the Ford effect. Which is the initial value problem of the Navier-Stokes equation with minus B dot U plus pressure is 1/2 of absolute value of magnetic field equal to 0, and then the equation for the magnetic field has a Lorentz force with a Ford effect, which is rotation of B times B equal to 0, and then double divergence free condition in the T is positive, and the X is whole space. And where the sigma of H is just a constant, just coupling constant and regarded as 1. So this equation appears in the some reconnection of the magnetic field around the sunburst or something, appears in many areas. And then people think about this equation, in particular the Dongho chair and Maria Schoenbeck. Consider the decay of solution 2018 JD. And in particular, the Dongho Chai and his former student Ji-Hoon Lee also consider the existence of solution, existence and uniqueness and blow-up criterion for this equation. Now we can introduce two kinds of scaling, because this equation is not a scaling invariant. If you consider the sigma h is equal to 0, which is just the usual MHD, viscous MHD equation, then we have an invariant scale, which is u lambda equal to lambda times u lambda square t lambda x, and b lambda equal to lambda b lambda square t lambda x, and pressure is lambda square, where the lambda is a free parameter, positive parameter. And then lambda is positive. Then without the Hall effect, the equation is also invariant, this scaling invariant. So that, therefore, both of, by the way, I have to put the initial data. Sorry, I have to put the initial data. Okay, initial data. And then this scaling, under this scaling, the MHD equation is very good. By using a Koho-Tautolo argument works. However, if you add the Hall effect, then the scale is slightly changed. The U and P is the same, but only the magnetic field going to be without lambda. So it's just like the compressive Navier-Stokes equation, the density of compressive Navier-Stokes equation. However, of course, this B equation is parabolic type, so you may obtain a much better result than theirs. And indeed, Jai and Lee obtained the equations, local existence, and well-posedness. Where was that? Yeah. これ消した方がいいですね。また使いますか。In the function class based on the Sobolev space, and they are asking the question if they can enlarge the function class. And according, on the other hand, the Hall effect has a second order derivative here, and with a nonlinear term, which is a quasi-linear term. So the maximal regularity may apply for that equation. So we consider the existence and uniqueness of solution, the space where both scaling is invariant. Oops. I'm sorry. そうか、こうするのか。はあ、べちゃべちゃになっちゃった。どうしようもない。I don't know how to do it. Okay. So both scaling. We need to think about both scaling. So we think about the solution inside the both scaling is invariant. So which means that function class is much tighter. Then the result is the following. Okay. It is theorem number, I think, 5. Shimizu myself. It is still preprint. And suppose that you note this belongs to a vanishing mean oscillation, -1. And then B note, they are the initial data. I should write the initial data here. I hope you understand. Then this belongs to a negative BMO intersection BMO. slightly higher regularity required. And besides, the initial data is small. Vanishing oscillation, -1 plus BO vanishing oscillation, -1 intersection BMO is small. Then there is the unique solution to this whole MHD equation. Solution. Actually, this is mild solution. Satisfying that the regularity is just like a continuous, bounded continuous, the fourth time in VMO, sorry, inverse -1 is yes, is L2 R plus of, sorry, VMO, V vanishing oscillation tilde, and V is also, this is bounded continuous function, or VMO, negative VMO, intersection of L2 or VMO, first order derivative is here, and that satisfy the regularity estimate, bounded. This is just like a cohort-artery estimate with the derivative. VMO, inverse intersection VMO, with the derivative of magnetic field as above, but that regularity is slightly higher because we want to include the higher regularity point with pressure. Let's see, pressure L2, VMO. Inverse is finite, some constant, very small constant. This is our main result. So let me show that the argument is quite similar to the cohort-artery for the Navier-Stokes part. Because we want to use the X is the supremum of continuous in to U. Sorry, VMO inverse with maximal regularity norm with the supremum of T1/2. The cohort-artery use the infinity space here, but actually you can relax a little bit to BMO, which is done by Iwabuchi and Nakamura, Happy and DIE, in 2014 or sometimes. And then is the same things with the magnetic field, with the same. Magnetic field with the external, this one, the derivative of V over L2 VMO tilde. We are using that kind of norm and then can control the velocity part by using the exactly similar estimate for the cohort-artery. But the highest regularity part for this part, we simply use the maximal regularity for the bounded mean oscillation. And then 3 minutes? Still more. So one important thing is that we need to somehow use some special structure of this nonlinear term, because we are using the negative power of the function class. We have to be careful on the bilinear estimate. And indeed, the bilinear estimate, we can prove such kind of bilinear estimate, which is the last proposition, proposition 6. It just only show the bilinear estimate. The assumption is that f and g has a certain regularity with the divergence f and the rotation g is both free. Therefore, the multiplication of both function has a special structure, so-called the divergence rotation free structure. Then, if you take this maximal regularity norm, negative one, can be somehow controlled by this kind of estimate also used by Yabuchi Nakamura, but they didn't use the divergence curve structure. This one, what is this? The continuous of sorry, this is everything just BMO. Vanishing mean oscillation. I'm sorry, my handwriting is horrible. And also some other terms, which is, let's say, only the above term is not quite sufficient. Therefore, we have to add with the supremum of t square root of u g. And then this can be bounded mean oscillation. And t is on R. And by using this bilinear estimate, we can somehow handle the last term by using the formulation of the mild solution. And this can be, then this proof is almost done by small data global existence. My final remark is that because this equation is not scaling invariant, this function class is not invariant scaling. So that I think that the local existence of well-posedness is also true in the almost same space, but I'm not quite sure yet. Okay, thank you very much for my kind attention.
So, can you also have other integrabilities than 2?
Yeah, okay. You mean maximal regularity?
Yeah.
Yes, okay. The reason why I choose the second L2 is because the initial data going to be belongs to BMO. If you exchange the power, then that's going to be changed into a looking trivial space with suffix theta or something. So that could be changed. This is possible actually, but this formulation is not really easy because subtraction argument is just this is very good for the integral parts. That's why we choose a 2. But if you want to choose a theta, for instance, then you use let's say the potential estimate like Stein's. The Stein's textbook actually can cover that part.
And you also, now at your application,
Mm.
you have initial data in the negative space, right? Like the BMO -1.
Yes, those are negative one, yes.
If you have regularity theorem, you have like in the first order BMO.
Okay, so if you put a negative one here, then the derivative is just one first order, right? Because if you put the negative, that's also possible actually. Then just change everything, just negative one, whatever. Then this is going to be, let's say, negative one, which means BM1 first derivative, right? And then right-hand side is going to be without the U0, without derivative with negative one, something like that. So you can apply that estimate. By the way, the old estimate is possible for the BMO too. However, the continuity at the initial data is wrong. Only a weak star convergence, like the Tuesday's short talks, Professor Sam, he did it. Yeah.
The question? Is there any chance to adapt this into A?
Adapt to it?
Do you think that you can adapt the domain case?
A domain case? Yeah.
Case -1.
Yes, yeah, I'd like to really think about it because the Giga has already proved the analytic semigroup. And if we, let's say, introduce the different type of definition, the subtraction might be, I'm not quite sure, but if we use a semigroup of heat equation in bounded domain with a certain boundary condition, then I think the equivalent norm is also possible. And I don't know if this is really BMO or not, but that's possible, at least.
duality on maximal regularity in Hardy type spaces, the H1?
Hardy type, yeah, I think that's true. Yeah, but I'm not. Yeah, actually, one of my former students tried to do it, and now I think still think about that. You know, the time Hardy spaces has already done by I forgot his name, the German person anyway. They know about that. But the space Hardy one, I'm not quite yet sure, but I think this is possible. Yeah. But it's not going to be a dual of this space. This is kind of different, so that if you use this kind of arrangement, that's almost a direct result. But this is not Bohana space.
All right. Thank you, Stokes.
Thank you very much.